This is topic C, part 2, and we'll be looking at an application that involves using antiderivatives. We'll be solving a simple differential equation. You probably know that differential equations is actually a whole course. We'll only solve a very specific type. But in general, a differential equation is nothing more than an equation that contains a derivative. The kind we'll look at will always be this type, where it starts with dy dx equals. And so in this case, my differential equation is dy dx equals 2y minus 3. I'd like to start by saying, find the general solution and graph several samples. Let's do that much first. All right, typically we think of dy dx as simply notation, not a real fraction, but it's useful to us in this situation to imagine it like a fraction, and we can go ahead and multiply to bring the dx over to the right-hand side. What this allows me to do is what's called separate the variables. The y is on one side and everything with x is on the other. I now follow one of my cardinal rules of algebra, which is I can do whatever I want to do, pretty much, to an equation, as long as I do it to both sides. I'm going to choose to do an antiderivative to both sides. On this side, the variable the integrand here is really just 1, and the variable of integration is y, so we'll get 1y. On this side, the integral of 2x would be x squared minus the integral of 3 would be 3x. And I'm going to have that plus c, that constant of integration. Let's talk about a couple quick things right there. First of all, notice that the dy and the dx are very important parts of performing the antiderivative. I have to know the variable of integration. Otherwise, for example, when I integrate constants, I wouldn't know that this one integrates to 1y and that that one integrates to 3x. So you may think the little dy and dx aren't very important in the notation, but in fact they are. The second thing I'm going to mention is technically there would be a constant of integration on both sides. Right? There would have been a plus c on this side and another plus c on that side. Maybe I could call that one C1 and that one C2. What I want you to imagine that we've done is just subtract the C2 minus the C1, and so I end up with a single constant, which I'm going to list on the right-hand side. I'll follow that pattern every time I solve these kinds of differential equations. All right, so our solution, y equals x squared minus 3x plus c. This is what's known as the general solution. It's got the plus c in it. And it says here to graph several samples. I'm just going to go ahead and do that on Desmos. So when we graph, we'll go ahead and graph y equals x squared minus 3x, and then we can pick some different values of c in order to tell what this looks like for various c values. So here's my Desmos graph, and again I'm going to start with y equals. It was x squared minus 3x. And I'm going to go ahead and put in plus c, and I'll tell Desmos to add the slider on c. So you can see right now the graph shows c equals 1. If I adjust the c value, notice that all that's happening is this graph is just being shifted vertically. That makes sense. That's what a constant add-n does to a function. So, let's see, the c equals 0 case, if I can get it to stop at the right spot, there we go, looks like that. And then the graph just shifts up with a positive c and down with a negative c. So, in terms of graphing several solutions, I would just have the same parabola moving up and down for different values of c. All right, the next thing we're being asked to do is to find the particular solution given an initial condition, f of 0 equals 5. An initial condition is nothing more than an x and a y value that have to be on the graph. So this graph has to contain the point x equals 0 and y equals 5. If I plug those into my equation, I'll be able to solve for a specific c value and get what's called a particular solution. So I'm going to put in my initial condition, x equals 0, y equals 5. And that means I'll have 5 equals 0 squared minus 3 times 0 plus c, or simply 5 is equal to c. So if I put that in, I'd have y equals x squared minus 3x plus 5. That is the particular solution that goes with the initial condition. Specifically, since we have to go through 0, 5, notice that's going to pick out one specific graph out of this whole range of infinitely many possibilities. Specifically, it chooses the graph that contains that point, 0, 5. So out of all infinitely many possible c values, we now have one particular one that represents our solution. All right, here's an application of a differential equation. A ball is thrown upward from a height of 12 feet with initial velocity 20 feet per second. Find the position function and the time the ball hits the ground, assuming that gravity is the only force that acts on it. All right, well, I'm going to start by saying I know that the acceleration, which is gravity, is, let's see, if we're in feet, that would be negative 32 feet per second squared. All right. Acceleration is already the derivative of velocity, so this means that dv dt is negative 32, and I've now turned my acceleration statement into a differential equation. Let's do what we did before. I'm going to bring the dt to the other side. And then I'll say I'm going to solve this differential equation by taking the antiderivative on both sides. This is the antiderivative of 1 dv. So that's going to give me 1v, or just v. I know there's a plus c, but I'm going to incorporate it into the other side. Here I've got negative 32 dt, so this constant integrates to negative 32t, and I'll put the plus c over there. All right, initial velocity is 20 feet per second. So I'm going to use that as my initial condition to solve for c here. What that says is that initially, at time 0, the velocity should be 20. So v is 20 when t is 0. And I can see that 20 is equal to the c value. So I'll rewrite my velocity equation as negative 32t plus 20. All right, I'm halfway there. What I really wanted, though, was the position function, so the height. If this is v, the velocity is the derivative of the position, ds dt equals negative 32t plus 20. So now I have a new differential equation to solve. I'll take the dt and move it to the other side. So ds is negative 32t plus 20 times dt. And once again, I'll solve my differential equation by doing the antiderivative on both sides. The antiderivative of 1 with respect to s would be 1s, or just s. And over here, I'm going to get negative 32 times t squared over 2 plus 20t, since we're integrating dt. And I'm going to choose to put the plus c on that side. So I have negative 16t squared plus 20t plus c. All right, we need to solve for this c also. And let's see. When the ball is first thrown, so at time 0, it's at a height of 12 feet. I'll use that as my initial condition for the position. At time 0, position or height is 12. So if I plug that in, 12 equals negative 16 times 0 squared plus 20 times 0 plus c. And I find that 12 is equal to c. So my final position function is s equals negative 16t squared plus 20t plus 12. And that was the first thing that I was asked to find, the position function. The second thing we were asked to find was the time when the ball hits the ground. So we know we'll hit the ground when the height, s, is 0. And I don't believe that's factorable. You can try, but I'm pretty sure it's not. So we would have a choice of solving it either using like a quadratic formula, or you can solve it graphically. Doesn't really matter to me how you do that. In fact, since I've got Desmos right here, why not use a graphical method? If I go ahead and graph my position function, s of t is negative 16t squared plus 20t plus 12. It's not a great window. I could fix that a little bit. I don't need nearly as much on my x-axis. Let's just go maybe from like negative 5 to 5. We have plenty. But I needed to go up a little higher in the y direction. I'm going to go up to 20 on the y-axis. There we go. That's a little bit better. I can see that this parabola has zeros at negative 0.443 and at positive 1.693. Now, since t represents the time since the ball was thrown, I wouldn't be interested in a negative t value. That was before we ever threw the ball. So I'm really interested in this positive one. T equals 1.693. All right, that brings us to the end of topic C.